This is lecture 22. Let's wrap up our discussion on the LNA, or at least the narrowband LNA that we were discussing with regards to the treatment of noise, gain and matching, right? We haven't yet touched upon distortion, but as long as we are interested in evaluating an LNA on these three parameters, that is noise, matching and gain, this narrowband inductive degenerated, source degenerated configuration seems to be a decent choice, right? So yeah, so what we have here, a quick wrap up. So this is the input side of your LNA, the small signal input side of the LNA, right? And the output side, if we want to get a gain, we saw that we can also wrap a inductor at the output, right? Also, so what did you observe? You observed that the input impedance Zin is essentially this is not, sorry, let me redraw. So this is the one that we have, LG, LS, CGS. So we saw that the Zin is essentially J omega LG plus LS plus 1 by J omega CGS plus omega T times LS at resonance at omega naught is equal to under root LG plus LS CGS. My Zin becomes omega T times LS, right? So which means that I am getting, if I choose omega T times LS is equal to RS, which is 50 ohm. If we do not have any transformer and all those impedance transformation stuff, then then we see that matching is enabled. We also saw that the effective GM, right? GM effective was essentially 1 over RS omega T over omega, right? Okay, so now the effect, by the way, when I say effective GM, I am input of the effective GM is the it does not contain the effect of RS, right? So if you contain the effect of RS, that is from the source, then there will be a factor of 2 that you have to account for. Okay. So this and we also saw that the noise figure or noise factor was 1 plus some extra stuff, right? 1 plus some delta, where this delta is essentially proportional to omega by omega T whole square times GMRS, right? So again this also gives us a design variable, that is, if we bias our transistor for as high as omega as possible, as high omega T as possible, then we are good, right? So then we can get significantly low noise figure, and in fact This type of configurations are known to give you very good noise figure. I mean, easily sub 3 dB, less than 2 dB noise figures you can get with a decent power consumption. Okay. Okay. So now there are a couple of things that we need to touch upon before we move on from this LNA. One is, what about the load side? What about the drain side? So till now we have assumed is that everything we have done is analysis is on the basis of short circuit current at the output, but ultimately this current has to flow into some load, right, and then generate some voltage. In one of the previous lectures we saw that using resistors is probably not a good thing because you are going to have a lot of headroom issues, right? And now we also know that using resistors is not particularly a good thing if you are noise sensitive, right? If your circuit is noise sensitive, you ideally won't want to use any resistors. So inductors was a good choice. An even better choice, right, especially if it's a narrow band LNA, is an open circuit, right? Now what is an open circuit? An open circuit can be manufactured by having a infinitely large inductor, or I can even have a resonant open circuit, right? What I mean by that is, if you have an inductor and a capacitor at resonance, is a short circuit, correct? It's a series inductance which gives you a short circuit. But if you have a inductor and a capacitor, a parallel combination of inductor and capacitor between A and B, what do you get? So essentially this is, whenever you have things in parallel, it is easier to evaluate them in admittance mode, right? So this is j omega c and this is 1 by j omega l. So your admittance effectively is your YAB is essentially j omega c plus 1 by j omega l, which is nothing but 1 minus omega square LC by j omega l at omega equal to 1 by under root LC. Your YAB at omega equal to 1 by under root LC is equal to 0, implies that your ZAB is equal to infinite. You have an open circuit, right? So an open circuit is an awesome thing if we want to get a gain, because ultimately I can then replace my output stage with a inductor and a capacitor, and let me call this LD, let me call this connected to the drain, so let me call this LD, and this is CD. Okay, but as we all know that nothing is open circuit and nothing is short circuit in reality. The reason is all these inductances and the capacitances, they come with some sort of loss, right? For example, the capacitance CD will come with might come with a parallel resistance. Similarly, an LD will have a effective series resistance. So I can essentially model everything as some RLC, right, where it is implied that this is a parasitic resistance associated with the LC tank, right? We will, in one of the later lectures, where we'll talk about passives, we'll see how to model this RLC given certain losses associated with the LC. But for the time being, we understand that at resonance, the impedance that we will see will be equal to RLC. Okay. So now the question is, what happens to this? I mean, you will not be ultimately using this inductor this LNA in isolation, right? The LNA is going to feed the next stage, and what is typically the next stage of the LNA? That is generally a mixer, right? So now, when you have an LNA, let me now just simply draw the LNA as a voltage source and an resistance, a voltage control voltage source and the resistance, and you have a mixer which is operating at FLO. So there are a couple of things that tend to happen. One is, if you recall our discussion on direct down conversion mixers, or even for that, even super heterodyne kind of mixers or receivers, then you probably will you probably will remember that normally there is a capacitance associated between the LO port and the RF port of the mixer, which causes some feed through from the LO to the RF port, which essentially means that if there is a mixer here, so there can be a feed through from this mixer to the output of your LNA, right? So there can be, or let me call it an LO kickback. Okay. So now, why is it a problem? That is a problem. The way we have drawn this entire schematic, this is not a problem. But you should readily understand or appreciate the fact that there is a CGD capacitance which we have not been talking about, kind of been ignored inconveniently till now. Now, what can happen is, because of this feed through, right? So if this is, let's say, C mix, right? So based on this capacitance ratio of C mix and CGD, this feed through can come all the way to the input port of the LNA, and this feed through can be significantly high in amplitude with respect to the actual signal that you are receiving. So that can be a big problem. Another problem that can happen in this, but if we make an LNA having this particular configuration, is the following. Is that if ultimately we are designing this LNA for a large gain, right? So, or a reasonably large gain, which means that for some amount of swing at Vi, you are expected to have a decently large amount of swing at the drain of the transistor, which means that if you are not biasing the transistor properly at a sufficiently high drain voltage, then the transistor can go out of saturation. But that's not a problem if you are using an inductor for biasing, right? So what I mean is, if we have an inductor here, then by default the drain is at VDD, the maximum potential that you can have, approximately VDD. So going out of saturation is not a problem. But the problem that will appear is, so I will not prove this, but intuitively you can understand that just like this CGS capacitance is creating a real part of the impedance, similarly the CGD capacitance, which is between the gate and the drain, will also create some real part of the impedance and effectively affect the input match. Okay, so the problem with CGD is just twofold. One is you have a kickback of the LO from the mixer to the input of the LNA, and two, it can effectively disturb the input match, right? So can disturb So now, if you want to get a, without going into the very brute force analysis of this, if you want to get an approximate uh, idea about why this can affect the input match, you can basically, even though this is not a one-to-one example, but you can probably get an idea through this common topology. Let's say it is a grounded source configuration. This you have a CGD, and let's say you have an output capacitance. I call this CL, right? So what is the input impedance that you see here? If you recall one of the earlier lectures, so the Zin is basically 1 over Gm plus whatever the impedance is in feedback, that is 1 by j omega CGD, by the intrinsic gain of the transistor. Here the intrinsic gain, in the absence, if I neglect the effect of GDS, the intrinsic gain is Gm over j omega CL. This is Gm over j omega CL. So this basically is 1 over Gm1 plus CL by, right? So this is an approximate, right? So I should say approximately equal, right? So I mean, as you can see that even though this is not an exact, this is not exactly what is happening in the circuit on the left, but this kind of gives you an idea about, because you have a swing at the drain, right? Because if you have a swing at the drain, you essentially, because of the Miller effect, you kind of attract more current through the CGD capacitance, right? Because of this Miller effect kind of thing, you attract more current through the CGD capacitance, and you are also attracting current through the CGS capacitance. And the CGD, the current through the CGD capacitance is also a function of the swing at the output node, right? And because you are expecting the swing in a low noise amplifier, it's an amplifier at the end of the day, because you are expecting a lot of swing at the drain, right? Which effectively means that you, depending upon how much gain you have, you will end up drawing appropriate amount of current through the CGD, which was not supposed to draw any current if CGD were 0, right? So so one might say that, then reduce CGD, but reducing CGD is essentially means that I have to tamper with the size of the MOSFET, which will in effect hamper so many other design variables. So that's what we do not want to do. So what is the solution? The solution is, like many other solutions in analog circuits that we normally see, is we need to reduce the voltage swing here, right? So this we do not want to change. This is as is, but we want to reduce the voltage swing at the drain without changing the short circuit current, right? Without this current, I do not want to change. Okay, so this has to be Gm effective times Vg. This I do not want to change, but I want to change the swing, which essentially means that if I do not want to change the current, but I want to change the voltage, which means I have to, looking up, it has to be a low impedance node, right? Looking up, it has to be a low impedance node. So what configuration do you see? Do you know that low impedance, looking into its one of its terminals? It's obviously a cascode or a common gate or a cascode transistor. So just like one of our examples before, where we did the common gate configuration, we can put in a cascode where incrementally this is shorted, and then you take the output and give it to a, and in order to if we want to see the entire biasing circuit, this is similar to one of the cascode biasing networks that we had done earlier. So let me quickly use the same principles, and hopefully this will refresh your memory. So this is M1, this is M2. So this is my usual LNA. Obviously, the input that is coming from the antenna has to be AC coupled. Let me call this CC. How do I bias the input of M1, the gate of M1? Using the same principle as earlier. So I can basically take this, create a appropriate VGS from a diode connected transistor, and that VGS can be fed to the gate of M1, but obviously through another biasing resistor RB, because you do not want the signal current, the small signal current that is coming in. You want the small signal current to go through this path and not necessarily uh, through RB, right? So you would want to ensure that RB is much higher than what is the impedance looking in. What is the impedance looking in? Zin, or let me in this case Rn is RB plus 1 over Gm of M naught. So this has to be much greater than basically whatever impedance that what this is should be much greater than what the Thevenin equivalent impedance looking up, right? What is the impedance looking up? This is essentially 50 ohm due to, at resonance is basically the 50 ohm due to the antenna and the 50 ohm due to the input source. So it's basically Rs by 2, right? So if we ensure that this is greater than Rs by 2, then this RB will not load. Okay. What about the cascode? How do you bias cascode? Just like earlier, one of the earlier lectures. The biasing of cascode is not that critical as long as you have sufficient amount of headroom, right? So let's say this is VDD, this is R1, this is R2, and we also, if you recall, we also talked about the necessity of having this CCAS just to ensure that this does not, the capacitance, CGS capacitance of the cascode does not have does not end up shorting the gate and the source at high frequency. So that CCAS had to be sufficiently high to always keep the gate of the M2 transistor incrementally shorted, right? Okay, so this is CGS2, and this side obviously you have VDD, right? Now this is not sufficient because when the signal comes in, you have a swing here. That swing can percolate here, albeit like at a very attenuated at a very attenuated stance, but nevertheless, in order to ensure that you do not tamper the diode connected voltage that is generated by the swing that you are encountering, it is always a good practice to have a capacitance here C0 ensures the bias is stable. Also, what it does is ensures that the noise from M0, right, and noise from M0 is filtered. Because essentially the noise current that will get generated here will go into C0. If C0 is sufficiently large, and it will not contribute anything to the main circuit, right? Now, having said that, since we are discussing noise, what about the noise contribution of all the other all the biasing networks, right? So let's start with the noise contribution of RB, right? So, so what do I see in RB? So right now this is my network, and you have RB here. If this C naught is sufficiently large, then this is ground, right? And what is the impedance? I am neglecting all the LG and I mean the effect of LG and everything, because at resonance they will essentially uh, okay. So I am neglecting the effect of LG because the details due to LG might change, but the principle will still be the same, right? So now what is the impedance looking in this side? So if I assume, let's say I, instead of connecting it here, if I connect here, in principle nothing much changes, right? uh, but I mean the analysis becomes slightly simpler. So what do you see this side? What is the impedance? This impedance is RS, correct? So now what is the noise contribution due to RB? Or rather, let me basically say that adding RB, how does it affect your noise, right? Instead of having the effective noise contribution of RB. So if I am only concentrating on the noise voltage that is getting accrued across these two ports, right? So if I am concentrating on this noise voltage or noise power spectral density, what I will look for? I will look for effectively the effective real part of Zin, right? So what is the real part of Zin? That is RS parallel RB. So if RB is much greater than RS, not RS by 2 in this case, then uh, real part of Zin is approximately is equal to RS. Therefore, the effective power spectral density looking into the port, right? So SV because of Zin becomes 4 kT RS. So RB, the effect of RB does not come into picture at all, right? So essentially, in order to ensure that you bias your network without causing any disturbance, any additional noise due to RB, you have to ensure that RB is much greater than RS, right? What about the noise due to the cascode transistor? Okay, so let's look at the only the cascode transistors in isolation. So what I'll assume is that this is grounded, because the assumption is C cas C is much greater than CGS of the cascode. So C cas C is much greater than CGS cas. So you have CGS cas, or let me just say CGS2. Similarly, there is a parasitic capacitance associated with this. This parasitic capacitance can be the CdV of M1, right? Of M1, right? And all the other capacitances associated with this node, maybe a metal routing capacitance or parasitic capacitance. So everything combined is CdV1. Looking down, you have that you are looking into the drain of the MOSFET M1. So let's assume, to keep things simple, let's assume this is ground, this is open circuit, and I am interested in finding out what is the uh, effective short circuit current, right? So I'm interested in finding out what is the effective short circuit current. So I am interested in finding out what is IN out due to cascode only, and I understand this is my IN due to cascode, due to IN of due to M2. So I have to find out what is the contribution of IN2 at IN out. So So this is quite simple because at the source of this M2 transistor, right, uh, the only thing you have to understand is the amount of current that comes out of this terminal is the same amount of current that has to go in through this terminal. So if I can find out what is the amount of current that is coming out through this terminal, I am good. Correct? So let's see. So what? So this current is IN2 that is going into the terminal, and it has two ways to go. It can either go up, right, into M2, right? It can either go up or go down. And in fact, if since it has both paths to go, it will go either way. It will go both ways, but in a certain proportion. And what is the proportion? The proportion is basically the ratio of conductances. Correct? So I am interested in finding out what comes out of that box. I am interested in finding out what comes out of this box. So essentially, which is essentially the IN out. So your IN out is nothing but the ratio of the conductances, that is J omega CGS2 plus CDB1 divided by GM2, because looking up impedance to the source is GM2, plus J omega CGS2 plus CDB1. Correct? So times IN out. Okay. So if I can write it in a much like a neater form, so this becomes 1 plus GM2 by J omega CGS2 plus CDB1 times IN out. Okay. So which essentially means that your SIN out due to M2 is 4kT gamma GM2 by 1 plus GM2 by CGS2 plus CDB1 whole square by 1 by omega square. Now what is this GM2 by CGS2? GM2 by CGS2 is approximately the omega T of the cascode transistor. So this is approximately omega T, but need not necessarily be. It will be smaller than the omega T because the denominator is larger. So essentially I can basically say that SIN out due to M2 is 4kT gamma GM by 1 plus omega T for the second transistor by omega whole square. And obviously, I mean, everything we are designing so that omega, I mean, as you can see that in this case, if you are biasing your transistor in such a way that your omega T2 is much greater than omega, then this is approximately equal to 4kT gamma GM omega by omega T2 whole square. But mind you, the omega T2 is not only the GM by CGS, this is GM2 by CGS2 plus the CDB of the bottom transistor, right? Okay. So now what is the takeaway? The key takeaway is that, again, just like before, if you do not want the effect of noise from the cascode transistor to be dominant, then you have to ensure that you bias your cascode transistor also at a maximum as high as omega T as possible. But sometimes this is not possible because biasing cascode transistor at a higher omega T entails, or biasing any transistor at a higher omega T entails that you'll have to bias it with a high overdrive voltage, right? Now when you are putting a cascode transistor, you are already short of overdrive, right? Because you have eaten up some of the headroom. So that's a design trade-off that you have to deal with. Okay. What about the noise contribution due to R1 and R2? So clearly, if C cascode is much high, then this is also get filtered out. You do not have to bother too much, right? But in anyhow, you should be you kind of get a rough design guideline as to how to go about biasing your transistors when you are looking forward to low noise applications, right? Okay. So now it is about time we start looking into the part of RF circuits which we have been avoiding till now, that is the effect of distortion. Now what is distortion? Distortion, as the name suggests, is if you have in an LTI system, if you have an input and you expect it to get amplified by factor of A, right? So for example, if I say that I have an LTI system which has an amplification factor of A, or let's say, let me just say that amplification factor of 10, then if I have a sinusoid, then output will also be amplified by a factor of 10, right? It does not say that if the amplitude of the sinusoid is different, the output will get amplified by a different amount, right? But what happens if the amplification factor is or the response of the system is also dependent on what is the input amplitude? For example, if your amplification is such that, if your amplifier is such that for a small input, okay, so let me rephrase. So if your amplifier is such that it's V0 over Vi, Now note that nothing is time in this case. Your V0 over Vi characteristic is not a straight line. It's not a straight line. It goes something like this. What happens then? So if your sinusoid, if your input is probably varying between these two, if your input is varying between these two blue lines, then your output will vary between these two red lines, right? And if you do not zoom in, and if you look from sufficiently large distance away from this curve, you probably will think that it is for equal increments of the input, you have identical increments in the output, right? But what if your input varies from here to here, right? What if your input varies from here to here? So clearly you will get some increments here. You are going to get some amount of increments within these two, some amount of increments when your input amplitude is within a smaller range, and a different amount of increment when your input amplitude is at a higher range, right? A very trivial example, or a very extreme example is, what if your V0 over Vi curve looks like this, and your input is supposed to vary between these 2 points, right? Your input varies between these 2 points. Then what is going to happen? You are going to see amplification or a linear response of the system for the inputs which are bounded by these two black lines. But moment you are going on the right side of the moment you trespass into the territory which is on this side or this side, you are going to see clipping of the input. Now clipping is an absolutely is an extreme phenomena, right? You might not necessarily wait for clipping to understand that there is the distortion has started to dominate. In most circuits, the in most analog or RF circuits, the effect of distortion starts even before you start seeing actual clipping. Correct? So we'll have to be which essentially means that we'll have to come up with a way of understanding, a mathematical way of understanding distortion, because it doesn't seem like we can visually understand what is the amount of distortion we are okay with, because when it clips, it's probably already too much distorted. But we need to understand that in a weakly nonlinear circuit where the clipping and clamping and all those bad things hasn't yet happened, but it is going towards clipping or it is going towards clamping, can we measure distortion in those scenarios? And there is a well formulated way of characterizing distortion in analog circuits and in RF circuits. In today's lecture, let me talk about the distortion in analog circuits in whatever part time that is remaining. In the next lecture, we'll take that into the domain of RF circuits, right? So to start off, is a resistor nonlinear device? Right? Clearly not. At least if we go by Ohm's law, right? An ideal linear resistor is not a nonlinear device, because I know that the current is V over R. So basically, for every linear increment of V, I get any linear increment of I. What about a transistor? So clearly, this is not a linear device, because of what? Because your IDS is some constant times VGS minus threshold voltage whole square, assuming square law, right? So in realistic MOSFET, this it's much more complicated, but assuming square law, this is your output current to voltage conversion. If input is applied alongside VGS, again speak if, right? Not necessarily you always apply input with VGS. You have so many configurations. So if input is applied alongside VGS, then your IDS is essentially I naught plus delta I, where delta I is the effective signal information, times beta times VGS naught plus delta Vi minus threshold voltage whole squared. I'm sure you have seen this multiple times in your analog circuit course, but I will still do it once. This is VGS naught minus threshold voltage whole squared plus 2 beta VGS naught minus threshold voltage times delta Vi plus beta delta Vi squared, right? So this is essentially I naught, so which means that your delta I is 2 beta VGS naught minus threshold voltage times delta Vi plus beta delta Vi squared. What is this? This is essentially what we call as GM, right? This is GM. So your delta I is the linear component, that is GM delta Vi, plus a nonlinear component delta Vi squared. Okay. So we have delta Vi squared. So what's the issue? The issue is, if delta Vi is supposed to be, let's say, Vp cosine omega naught t, right? Typically in an RF system, you will have a tone and you have signals around the tone. Let's assume cosine omega naught t is the tone. Then what is delta I? Delta I is Gm times Vp cosine omega naught t. This is what we expect, but you have another term which is beta times Vp squared cosine squared omega naught t, right? Okay, so what's the issue? So there is no issue with the first term, which is exactly what we want, but the second term I can decompose using trigonometric identity as 1 plus cosine 2 omega naught t, right? So now note that you had a system where the input is at a frequency omega naught. What do you get at the output? At the output you get omega naught, but on top of that you get two extra things. You get a DC term and you get a term at 2 omega naught, right? So this clearly is not that something that you expect from an LTI system. In an LTI system, if a input is at omega naught, output is at omega naught. All good. But in this case, you see that if your input is at omega naught, your output is also at twice omega naught. So what's the issue with that? So other than the fact that this is unwanted, right? But we would also like to understand what is if the impact of this Vp square by 2 times beta is large, what impact can it have? In an RF system, note that an LNA is followed by a mixer, right? And a mixer is essentially, if you recall one of the earlier lectures where we are talking about architectures, a mixer is not does not only contain an ideal sinusoid, it also contains harmonics of the sinusoid, right? It also contains, if the mixer is operating at omega LO, it will also contain terms of omega LO, 2 omega LO, 3 omega LO, and so on, right? So if your input of the LNA, if the output of the LNA has also terms of omega naught and 2 omega naught, right? So then the mixer output will also, the mixing operation will not only happen with omega naught and the various sidebands of omega LO, but it will also happen with 2 omega naught and various sidebands of omega LO, and that will basically down convert back into your baseband, right? So essentially what I am saying is, if I have a mixer now which also has omega LO and 2 omega LO, right, it will have all other components as well, but I am just making a simplifying assumption. Then the output, and you do a low pass filter. So the output, if the low pass filter, if 2 omega naught and 2 omega LO are nearby, omega naught and omega LO are nearby, so the output will have single components at omega LO minus omega naught, 2 omega LO minus 2 omega naught, right? Twice omega LO minus omega naught. So both of them can fall in band. It might corrupt your, signal, right? Not only that, now the output of the LNA, the swing at the output of the LNA is not just governed by the fundamental component. It is also being governed by your distortion components, right? So if the distortion components are significantly larger than the fundamental components, or even comparable to the fundamental components, then it can also saturate out the following stages. Okay. Additional problem is, you see that you are getting an additional DC term. What does DC correspond to? DC effectively means bias, right? It's a bias voltage, it doesn't change, is DC. But it seems like at a very top intuitive level, if you have a common source kind of configuration, which also has a distortion associated with it, right? Then it seems like it can change the bias level at the output of the LNA, right, or output of your block. So there are several other things. I mean, as you can see quickly, even without going into details of circuit design, we understand that distortion is a bad thing, right? So in whatever time that is left in today's lecture, I would like to give you a quick idea as to what is the simplest thing that you can do to reduce distortion. There are many other advanced methods to reduce distortion, but a circuit designer's 101 guide to reduce distortion is the following. All you have to do is appreciate the fact that I would like to ensure that the distortion laden components, the strength of the distortion laden components are smaller than the fundamental component, right? So what is in the example that we just did, what is the strength of 2 omega naught? That is Vp beta square over 2, beta Vp square over 2. And what is the strength of omega naught, which is desirable? That is Gm Vp, right? Okay. So what we ultimately want to do? We want to ensure that the strength of 2 omega naught becomes much smaller than the strength of omega naught. Now, before we proceed, the important, you would have already noticed that the strength of 2 omega naught increases quadratically with the input amplitude, whereas the strength of omega naught increases linearly, right? So, so for every 1 dB increase in input, your 2 omega naught component goes out by 2 dB, whereas your omega naught component goes up by 1 dB, right? So not only that you are getting distortion, the effect of distortion is much more pronounced than the effect of distortion laden components are much more pronounced than the fundamental component, right? So that is why we have to ensure that by design the strength of 2 omega naught is less than omega naught, right? So what can we do? So basically I say this is strength of 2 omega naught, let me call it harmonic distortion component 2, right? And this is the fundamental component, which is harmonic distortion component 0. So what is Hg2 over Hg0? This is beta over 2 by Gm, right, times Pp. Okay. So what is beta? Beta is whatever is not in our control, that is mu Cox by 2 and so on, right? So we'll just keep it as beta. So this becomes beta over 2 Vp times Gm. What is Gm? Gm is in whatever your Gm is 2 beta times overdrive, right? So this is 2 beta times VGS naught minus threshold voltage. So your beta goes off. So you get Vp over 4 1 by P overdrive. So among this, what is the design variable? Clearly Vp is not a design variable, because if the input is directly applied to VGS, you cannot really expect the input to go down. So the input remains the same. But in other words, for a given input, if you have to reduce distortion, what you need to do? The only design handle you have is V overdrive, right? So to reduce Hg2, increase V overdrive, right? So as you see that increasing V overdrive is equivalent to saying that you are biasing your transistor at a higher and higher omega t also. So biasing it in analog and RF circuits, biasing a transistor with a higher overdrive voltage has benefits with regards to having faster frequency of operation, reducing the noise, and also reducing harmonic distortion, right? The only disadvantage that you will have if you want to bias your transistor with V overdrive is you will run out of headroom, right? Note that in this context we have not talked about, in this current context we have not talked about what happens if you run out of headroom, because if you run out of headroom, then the distortion will not appear because of the input swing. It will start to appear because of output swing, right? So in the model that we have just taken, we have assumed that the transistor is always in saturation, right? And the distortion is only due to the VGS nonlinearity. We have not taken into account what happens if the signal swings and ultimately your transistor can go out of linear saturation region also, and that will also cause distortion, right? So this increasing V overdrive can only help if your design is not limited by the output signal swing. If your design is limited by output signal swing, then this will not help. So essentially, when you are designing, you have to identify whether your distortion effects are due to the input, due to distortion of the current, or because of the distortion of the output voltage, right? Okay, let's stop here.